Okay, so come to the second point. So about Frobenius splitting. So first I will give the definitions and some easy constructions you can do just playing with definitions, and then I will present some consequences on the cohomology of Frobenius split variety. So first, basics, say. So let's fix the notation again. K now is an algebraic closed field of characteristic P positive. X will be a K scheme. So we assume implicitly separated and of finite type. And F is the absolute Frobenius. So let's say I'm going to write the definition there. Maybe this one. So the main definition is, so first, X is said to be F split for Frobenius split if the pullback morphism from OX to push forward of OX splits as a map of OX module. That is, if that exists, phi from the push forward of OX to OX such that phi composed with the pullback by F is nothing but the identity. The second definition, you consider Y a closed subscheme, a splitting phi of X is said to compatibly split Y if phi maps the push forward of the ideal sheaf of Y into the ideal sheaf of Y. So I will say a few things in a few minutes about that. And as you may imagine, let I1 up to IM in X be closed subscheme. Phi is said to compatibly split IY, YI, Y1 up to YM if for all I phi maps the push forward of the corresponding ideal sheaf into itself. Okay, so at least two remarks. The first one is the opposite inclusion is always true. ideal sheaf of Y is always contained in the image of phi, since for any local function vanishing along Y, f is nothing but phi f to the power p, by definition of the splitting. So this is always true. So in fact here we have an equality. And the second one is if Y is compatibly split by phi, it implies that if phi compatibly splits Y, then Y is split, Frobenius split. Phi induces phi bar from the push forward of OY to OY. So maybe the first lemma, if y1 up to ym are compatibly split, so is their intersection and their union. Okay, any union, I mean scheme theoretic union. Okay, so for instance, for the union of y1 and y2, the ideal sheaf is exactly the intersection of the two ideal sheaves. So in particular, phi maps this ideal sheaf into the corresponding intersection. But this is contained this is really a formal consequence of the definition, so there is essentially nothing. So lemma 2, any irreducible component of an F split scheme is split. So I'm going to prove this assuming something I'm going to prove later on. So let, for instance, write X as X1 union X2, where X1 is an irreducible component of X, and X1 is not contained X2. Okay, so you need to prove that phi is always a splitting of X. Phi of the ideal of X1 is contained in the ideal of X1. So you look at, that this is true, and you restrict, sorry, you look at this image on x1, on x minus x2, so this has to be a dense open subset in x1, and you look at the same here. So I claim that there is an inclusion because both are 0. So you get at least that phi map the ideal of x1 into the ideal of x1 with its reduced structure. But we will see that any F split scheme is reduced. So now I'm going to look at an example in a very particular situation, very simple case, the case of the affluent space. So first, just observe so we want to understand what the splitting is. So remember that this one is nothing but OX as a sheaf of abelian groups. So the splitting of X is an additive map from OX to OX phi, such that first phi maps the constant function 1 to the function 1, and such that phi is OX to the power p linear, that is phi of fpg has to be f phi of g for fg local function on X. Okay, this is just these things. So let's see what happened in the case where X is an. So the claim is that getting a splitting yes, the splitting of X is equivalent to getting a splitting of the p-power map at the level of the polynomial ring. So the only thing that is not completely clear is that giving such a map, can we construct a map of sheaves? But this is you don't have any choice. If F and G are in K of T1 up to Tn, you define phi of f over g to be phi of g to the power p, g to the pi 1. I should remove, not say this, but so you see that you don't have the choice. You need to use this formula. So you can extend such a map of from the polynomial ring to something to the shifts of functions on the affine space. So, and now since you want the linearity modulo Rx to the power p, any such map is uniquely determined by its value at the monomial Ti, where I is I1 up to In, and I is non-zero, because we know that phi of 1 has to be 1, so this is fixed, and ij are less or equal to p minus 1. And conversely, I mean, so in particular, choose phi of Ti equal to 0 for I different from 0 and ij less or equal to p minus 1, you get the affine space is split compatibly with the, how do you say this, with the coordinate subspaces. I mean, if y is given by the vanishing of some of the coordinates, you check that this splitting compatibly split such a sublinear space. Okay? So in fact, this is there is a more general result saying essentially that in the smooth affine case you get nothing. Proposition. So let X be a smooth, affine K variety, and let Y be a smooth subvariety then there exists a splitting of X which compatibly splits Y. Okay, exactly as in the affine case and in the coordinates subspaces. So essentially the proof is to reduce to this case. So you consider, let's say, let R be the ring of a function, the ring of global function on X, and I in R be the ideal of Y. So remember what we have said here. So you consider now M. So this will be an R module. The map from R to R that are additive and such that phi of f to the power p is f phi g for all f and g in R. So this is not really a splitting. One condition is missing, the fact that phi maps 1 to 1. Okay, if you add this condition, this is no more R module. So now M is an R module. The structure is given by, if you have lambda phi of something, it's just phi of it's just the multiplication. There's nothing to say. And the point is that this is an R module of finite type. And because of this condition, such a map phi is completely determined. Phi is determined exactly as in the case of the affine space by its values at generators of R as an R to the P module. So we saw that yesterday that the Frobenius is finite and flat, and as a consequence, we know that R as an R to the P module is a finite module. Okay, so you choose a finite set of generators, and you see that R is a finite type of R, say. So we need to consider another one. Mi is just the map phi in M, such that phi of I is containing I. So this is a sub R module. So now we can introduce the evaluation map. From Mi to R that maps phi to phi of 1. Okay, so the only condition that is missing to get a splitting of X that compatibly splits Y is just to impose phi of 1 is equal to 1. Okay, so we are only interested in the fiber over 1 of this map. So this is R linear. And the claim is there exists a splitting of X but compatibly splits Y if and only if epsilon is on 2. Okay? But this can be checked after completion at the localization of R at all maximal ideals, but R is assumed to be smooth, so we are reduced, may assume that R is a power series ring and I is given by the vanishing of, say, the first coordinate. Okay? So essentially, we are reduced to the case of the affine space. This is exactly the same computation. I mean, you set phi of the sum of over I lambda I t to the I to be exactly the sum for those i's that can be divided by p 1 over p t I over p. This is exactly the formula you get. Yes? One, 2 minutes. It depends on the degree. You will see. If the degree is prime to the characteristic, it's okay. Okay, so now, again, a few remarks playing with the definition. So the last lemma before going to the consequences. The first point is obvious. Let X be a split scheme, and Y in X be compatibly split. Now for every open subset U in X, U we get a splitting of U which compatibly split Y intersected with U. So more interesting thing is the converse. So conversely, if U is a dense open subset and X is reduced, and if phi, so we assume that phi is globally defined as a linear map from the push forward of OX to OX. This one is such that phi restricted to U is a splitting of U, then it is a splitting of X. Then phi is a splitting of X. And similarly, if Y intersected with U is dense in Y, and if Y is assumed to be again reduced, and phi restricted to U compatibly splits Y intersected with U, then phi compatibly splits Y. So the case of, in some sense, we want to remove the fact that phi is defined at the level of X. Now let X be a normal variety, and let U be an open subset such that the codimension of the complementary is greater or equal to 2, then any splitting of U uniquely extends to a splitting of X. And the last point to answer your question, consider now a map from, say, from X to Y. So a proper, no, not yet. So a morphism of K schemes such that the pullback by F from the function on Y to the function on X splits as a linear map. Then if X is Frobenius split, so is Y. Moreover, if this pullback by the morphism F is an isomorphism, And if Z in X is compatibly split, then you can consider the scheme theoretic image in Y is compatibly split as well. So essentially we will use this last point in the case of a birational morphism, starting with something singular, and X will be a non-singular model on which we have an NF control to conclude that Y is compatibly split with a lot of things. So for the proof, so it answers your question. If the degree of the, if you consider a finite morphism, if the degree is prime to the characteristic, then you can split this. In that case, it's correct. So the proof. So one is obvious. For the second point, phi is already defined, so the only thing is to see that phi of the constant function 1 is exactly 1, but we know that this is true at least when restricted to u, and as we are assuming that x is reduced, we are done. And similarly, for the second point, it's exactly the same. Okay, so for the third point, so you now let say let psi be a splitting of u, and denote by I the inclusion of the open subset. So you know that since X is normal, at the level of sheaves, the push forward of O of U is exactly O of X, and it means that essentially the rational function that is regular in codimension 1 has to be regular. So this is exactly the meaning of this, say, formula. So you can define using psi a splitting of X. So you want to define a map, say at least an additive map from OX to OX. So you start with a local function, you restrict to U, you apply psi, you get a function on U, and you extend to X. This is well defined. This is OX linear, since say call it phi, since phi restricted to U is psi is OU linear, and you get the desired splitting. So for the last point, you play essentially the same game. So for the proof of foo, select phi be a splitting of x. So you want to construct a splitting of y. Okay, so the first thing you can do, you have a map from OY to the push forward of OX. So this is exactly the push forward of the pullback by F. So recall that at the level of topological space, the Frobenius is just the identity. So this is exactly the same as this one. Now, using the splitting of X, you get a map from F upper star from this one to this one. This is push forward of phi, and since you are assuming that the pullback by F splits, you know that by assumption there exists something here. So call it say pi. Let pi be a splitting of from O. Okay, so pi is. So you have defined your phi, and you can check that phi is a splitting of y. So the last statement about the scheme theoretic image follows from the fact that if pi or F upper star is an isomorphism, then the ideal of y is of w is the scheme theoretic image. No, it's not written. W. So the ideal, it can be computed as the push forward of the ideal of Z. So you play with the definition and you see that W is compatibly split. So now some consequences of Frobenius splitting. So first, if X is F split, then X is reduced. So you will see that this one is very elementary proof. So again, phi is a splitting of X. So let F be a local nilpotent function on X. So for nu big enough, F to the power P to the power nu is the zero function. But now compute F to the power nu P to the power nu minus 1 as phi composed with the pullback. This is the identity. But now the pullback by the Frobenius is just the P power map. So this is phi of F to P to the power nu. So this is to be 0. So by induction. So X is reduced. So remark, in particular, if Y is compatibly split, then Y has to be reduced too. And if Y1 up to Ym are compatibly split, then we saw that the intersection has to be compatibly split. So the intersection has to be reduced. So for instance, you look at X is the affine plane. Y1 some line, Y2 some conic. So which one? Say yes. So X split Y1 is compatibly split with X because both are smooth. This is again true for Y2, but Y1 and Y2 are not compatibly split, as the intersection of Y1 and Y2 is exactly is non-reduced. Okay, so now I need a definition. A reduced scheme X is said to be weakly normal if any finite birational bijective morphism from Y, some scheme Y to X, is an isomorphism. So let's say example, if X is normal, then X is weakly normal. And as an exercise, the cusp is not weakly normal, but the nodal cubic curve is. So try to check this. So now the theorem. So this is not so hard, but call it theorem. If X is F split, then X is weakly normal. Okay, so for the proof. So let us consider a map F from Y to X, finite, birational and bijective. So the first prediction is, as F is finite, may assume X and Y are affine schemes. So let call A the ring of function on X and B the ring of regular function on Y. So, and define K to be the total quotient ring. So here X is not integral, so this is not the field of the fraction field of A, but you just localized with the all non-zero divisor, so we get exactly the same as if it were integral. You have an inclusion of A into B into K. So now let phi be a splitting of X, and observe that phi extends to an additive map from K to K, call it phi again, such that phi of 1 is 1 and phi of F, not F, it's not the ID now, X to the power P, Y is X phi of Y. Just as before, you define phi of X over Y to be 1 over Y phi of X Y to the P minus 1. Okay, see if Y is a non-zero divisor in A, for instance. So now we want to understand where this morphism is not an isomorphism. So you consider the conductor So this is the ideal of a function on X such that the multiplication by such function maps B into A. So at the level of sheaves, this is exactly the global homomorphism at our OX linear from the push forward of OY to OX. So this is an ideal of B contained in A. Okay? So let now W be the closed subscheme defined by I. So in X, what do we have? Yes, this is exactly at least at sets, the set of points where the map F is not an isomorphism, okay, of schemes. Now the claim, maybe an observation, phi compatibly splits W. Why? So need to see that phi maps the ideal I into itself. So take A in I and B in B. So phi of A times B is exactly phi of A B to the P. So as I is an ideal in B, this is in I. So this belongs to the image of A. That is A. Okay. So you get this for free. So in particular, W is reduced. Okay, as we saw before. And even, so this is exactly A of I, saying that A of I is reduced. And the claim is that Baymont I is reduced as well. And this is exactly the same proof as before, just using the extension of phi to k. So say if b to the power p is in I, then as b is phi of b to the power p, and as I is compatibly split, this has to be in I. So you use induction and you get the same. So we get two reduced closed subset. So we need to work a bit more. Say by by shrinking X if necessary, may assume that W is irreducible with generic point, say, eta. And now consider the localization of the Riemann function on y at eta. So this is a field. This is contained in another field. You look at the inverse image of W. Recall that F is bijective, so W is irreducible as well. And with generic point, the inverse image of eta. And this one has to be, you look at this, if I is a proper ideal in A, that is, if this morphism is not an isomorphism somewhere, then we get a non-trivial, purely inseparable extension of fields. Here again I use the fact that the map F is bijective. Okay. So this implies that there exists a function, call it lambda. So if necessary, again shrink x, a global function on y, such that lambda to the power p comes from the base, but lambda does not come from W. So here, maybe I should have written lambda restricted to the inverse image. I mean, you restrict your global function to the inverse image of W. You see this as an element in the ring, in the field. So the power p come from the base, but not the function. So you say that we have an extension of degree p. Okay, so here it is the same. Call it condition star. By the very definition of W, F is an isomorphism outside W. So the fact that lambda to the power p come from the base at eta implies that lambda to the power p itself come from x. Okay, so as function on y, lambda to the power p come from x, at least around the generic point of W. Now, lambda, again, is phi of lambda to the power p. If lambda to the power p is in this ring, as phi is a splitting of x, this has to be, again, a regular function at eta. This is a contradiction with this. Or, in other words, the ideal I is A and W is empty. So we get that F is an isomorphism. So the second interesting consequences of Frobenius splitting. Now I have said something about the singularities of X. I'm going to say something about the cohomology of line bundle of X. So theorem X again is an F split scheme. Y in X compatibly closed subscheme. I is a non-negative integer, and L is a line bundle on X. So first, if L to the power D has no cohomology in degree I, so if HI of X L to the power D is 0 for all D big enough, then this is true for all D. B, exactly the same argument. If the natural map from H node from X L to the power D to H node of Y L restricted to Y to the power D is surjective for all D big enough, then the same is true for all D. That is H node of X L is onto So I'm just going to prove the first part. On the second, this is very similar. So you consider again, so you get the pullback by the Frobenius. By assumption, there is a splitting here of. So you get an injective map. It is split. Now we tensor everything by L. So you get L F to the power F OX tensor with L. You use the projection formula. So this is nothing but F, the push forward of the pullback of L. And it's easy to see that the pullback of L is nothing but L to the power P, just looking at the transition function if you want. So in the end, you get something, an inclusion of L into these guys. In particular, the cohomology in degree I of L inject in the cohomology in degree I of the push forward of L to the power P, but the push forward of L to the power P is nothing that L to the power P has shifts of abelian group. In particular, this is enough to compute the cohomology. So this is isomorphic to the cohomology in degree I of L to the power P. Now you repeat. You see that HI of L injects in HI of L to the power P to the power nu for all nu greater or equal to 1. So for nu big enough, by assumption this is 0. So you get the conclusion. Exactly the same for the second point. As a corollary, we get co-derive vanishing for Frobenius split variety. Now let X be proper over K, and let L be an ample line bundle on X, and assume X is a split then hi of X with value in L is 0 for I positive. B, if Y compatibly split then the restriction map from H node L to H node Y L restricted to Y is surjective. And C, if X is equidimensional and cohomological, in particular if it is smooth, then the cohomology of the inverse of L has to be 0 as well for all now I less than the dimension of X. Okay, in particular, using Serre duality, this is the cohomology of L twisted by the canonical class. So you get co-derive vanishing for free. Okay, so just for the proof, so for the proof of A, you use Serre's vanishing. That says that hi of X L to the power D is 0 for D big enough and for all I positive. And then you apply the theorem. So for B, Serre's vanishing gives that hi of the ideal shift of Y twisted by L to the power D again has to be 0 for all D big enough and for all I. Now you use the exact sequence you guess. And the associated long exact sequence, so from x L to the power d, you restrict, and the cokernel is contained into the H1 of this guy. But this is 0 by self vanishing, so again you apply the theorem. And C is exactly the same under the assumption that X is Cohen-Macaulay and X is equidimensional. You know that L minus D is 0 for all D big enough. So we saw yesterday, more or less, that Codera vanishing theorem is not always true in positive characteristic. We also saw that sometimes there exists unclosed global one form. So here I can add a lemma. If X is smooth, say proper F split K variety, then all global one form are closed. And the proof again is very easy. So remember, one has an exact sequence with cokernel being exactly the exact one form. Here, this is a differential. Here, this is the p power. But we know that this map splits. So this implies that the push forward of OX is the direct sum of both. Now compute the dimension of this one. Using the splitting, you get that this is a HI of OX plus the HI of this part. But as I said before, this one is exactly the dimension of HI of OX, so this one has to be 0. Now, use the second exact sequence. Using the Cartier operator. So, sorry. The sheaf of exact form is contained in the sheaf of closed one form, and the cokernel is isomorphic to omega 1 by the Cartier operator in degree 1. Okay, so now you consider the long exact sequence associated to this, say H naught X, the push forward of B1, H naught X, the push forward of Z1, H naught of omega 1, cokernel map into H1 X push forward of B1. This has to be 0. This is 0, so this implies that in particular both have the same dimension. So all global 1 form have to be closed. So to finish, I will just state one more vanishing theorem, but I won't give the proof. So I will use it. Yes, before maybe just a few remarks. From the vanishing here, you can at least deduce that some varieties are not split. So if C is a smooth, proper curve of genus at least 2, then C is not Frobenius split. Okay, so indeed, in that case, the canonical class is ample, but the H1, if C were split, this would be 0 by the theorem, but the H1 by their duality is non-zero. You can do the same with hypersurfaces of degree more than n plus 2 in Pn, or n plus 1 in Pn. No, n plus 2, n plus 2. This is the same argument. Yeah, thank you. So in fact, most projective varieties are not split, but sometimes it happens. So the last theorem. What? Hey, sometimes yes, sometimes no. I mean, for elliptic curves, being F split is exactly equivalent to being ordinary. So you just have to look at the equation and to see if you get the one where it does. But I will explain this in my talk on Friday. I mean, I will look at a more general situation, but I will do the computation for the elliptic curves in my talk. So sometimes yes, sometimes no. And P1 always split. We will see this tomorrow. Theorem. So let F be a proper morphism of K-schemes. Let D, respectively E, be a closed subscheme of X, respectively Y, and let I at least one such that. So first, the inverse image of E, so E is in Y, is contained in D. So this is a set theoretically. It does it. So assume that the Ri of the ideal of D vanishes outside E. So you have to think about the case of a birational morphism. D is the exceptional locus, so you get this condition for free. And assume that X is split compatibly with D, then we get the relative vanishing of, in degree I, say, of the push forward of the ideal of D. So I don't have the time to prove this, but I will use it in the end. So again, we applied this to a resolution of singularities of Y. So I stop.